Hello and welcome to this first video in the series of how to use Threatray. In the first video we'll focus on detection and identification of unknown files. So Threatray provides a curated high-quality signature set for thousands of malware families ranging from cybercrime to C2 frameworks to APTs. In the course of this, we have also developed a novel and resilient signature technology that is based on code reuse, so we can easily track code regardless if it's known good or known bad, which in turn also means that we track frequently abused admin tools, lol bins, as well as a large range of legitimate binaries that comes in handy for many different use cases. So in this video, we'll be looking at three examples. The first one is basically a deep dive on Threatray on a cybercrime attack chain with Latrodectus and BruteRatel. Then secondly, we'll look at some APT backdoor that does DLL sideloading and involves the malware families Doplugs and PlugX. And then lastly, we'll look at another undetected APT that we will be able to attribute to HUILoader. Alright, so analyzing a file with Threatray basically gives you an analysis report, which we are looking here now, and this report covers detection, identification, intelligence, as well as behavioral aspects. We will now go through these different sections, and first up, on top here, we have an overview of the analysis results. We indicate that this unknown file that we analyzed is malicious and identified as BruteRatel and Latrodectus. On the right hand side here you can see the analysis type. So in this case here we had a dynamic analysis of this file on a Windows 10 machine. So that basically means the file was executed in a sandboxing environment, and there are many different types of analysis that you can do with Threatray. Not just dynamic ones, but you can also analyze files statically, you can analyze memory fragments, mini dumps, and so on. Given that this is a dynamic analysis, it also kind of explains why we can have multiple identifications here on a single file, and we'll dive a little bit deeper afterwards on how we got to multiple malware families. And we'll also see some behavioral aspects as part of the report later on. Now, Threatray is using different technologies to detect and identify malware. So on one hand, we have our unique code-based signature technology here, which identifies this analysis as Latrodectus and BruteRatel. On the other hand, we use OEM-based AV engine, which indicates that this is malicious here. And then we also have Yara rules that we wrote in-house at Threatray, whereas none of them actually matched here. Besides the verdict, which is kind of the combination of the verdict that you see on the left-hand side here, we also have this intelligence section on the right-hand side here, where we basically have lots of community Yara rules, and some of them matched. This intelligence section here doesn't contribute to the verdict you see on the left-hand side. It's purely intelligence. Of course, this is always helpful. Now, the report itself has two tabs that you see here, the binary intelligence tab as well as the full report tab. And we'll first focus on the binary intelligence tab. So, binary intelligence summarizes the important binary code that was extracted during analysis. And by extracted, we mean that suspicious memory was dumped during sandboxing, which we then analyzed further. So this, besides the submitted file, which you see here on the top, that is always here. So the reason we use sandboxing is quite simple. We want to get around typical packing and encryption or loading of additional components during execution. And this is basically only feasible if you execute it in a sandboxing environment. Again, you could also use static analysis if you already have unpacked code, or if you have memory fragments that might not run in a sandboxing environment in the first place. The full report here also contains more kind of behavioral indicators from the sandboxing run. Again, this is something we'll look at later on. So first up, we can see the analysis of the submitted file here on top. This one here is basically undetected. This is the reason for this question mark here. So none of the technologies I mentioned above has gotten or come to the conclusion that this is malicious or suspicious. Then the second section we have here, let me close this one here first, is the memory that we extracted with the dynamic analysis. So this is basically memory dumps that we have found from different processes. And you can see we have two memory regions here, one from Explorer, one from RunDLL, which are identified as Latrodectus and BruteRatel, as well as two memory regions which are just detected, but they don't have any identification. So let's first up look at this first memory region here, which is identified as Latrodectus, and dive a little bit deeper. So on each of these pieces of code that we show here, you can get additional details on how did we come to the conclusion that this is Latrodectus, as well as different intelligence around this piece of code. So here again, we kind of see these details on the verdict, same as in the summary above. Again, the summary kind of summarizes everything in the report. Here we're just focusing on this particular memory region where our code detection technology has indicated that this is Latrodectus. The AV has mentioned or detected this as malicious. And then again, we have a couple of community error rules, one of them indicating that this is unidentified 111, as well as, again, Latrodectus. Good. So let's focus a little bit on the code detections, which is really a unique approach of identifying malware as well as goodware, which I've mentioned earlier. And what we can see here is actually a very strong overlap between the code in this memory region and what we know and track as Latrodectus. So here you can see quite a good overlap between the code in here and Latrodectus, and hence we also identify that as part of Latrodectus. So this approach, compared to more traditional approaches, is not about looking at a few bytes or strings and then detecting a malware family based on that. We take a much more holistic approach and go deeper. As you can see here, we go as deep as looking at each particular function in the binary file and building our verdict based on that. This also kind of gives you a good intuition why this approach is resilient to modifications by the attacker. So evading this kind of technology would mean you would have to largely alter your code, and as opposed to more traditional approaches, not just changing a few bytes or strings. That, of course, kind of raises the bar for attackers to go undetected here. And furthermore, it's also not a 1 or 0 signal that you often have in an AV or with a YARA rule. It's a much broader spectrum, so even if certain functions go undetected here, we can still identify that. Good. So besides that, you can also see down here that we track benign code. So this is code coming from, let's say, standard libraries, compiler code, third-party libraries. We clearly identify that here. And this is also code that we don't use for any detection purposes. Otherwise, we would generate lots of false positives, because this is commonly shared code amongst malware as well as goodware. There are a lot more advantages of this core technology that we're using here based on code reuse. I will put a link down in the description, which links to an article where you can get more information on how it actually works and what it is useful for. But now, just purely looking at this example here, I'm highly confident that we are indeed looking at a memory region that is infected with code from Latrodectus. I have good confidence on code overlaps. I have an AV telling me it's malicious, and I have some community rules kind of pointing into the same direction here. Now, in the case of the platform here, you not only get a verdict on identification and detection here, you also get additional intelligence on every piece of binary code. And that kind of intelligence is based on searching for similar samples or similar code in a vast repository of samples. So Threatray itself has a constantly growing global threat feed, which encompasses 100 million plus malicious samples, and you can basically natively hunt through these samples. So hunting and also pivoting is more the subject of the next video. I'll be looking at that. However, in the context of identifying and detecting, intelligence sometimes can also lead us to good identification. And one type of intelligence that we have here is prevalence. So prevalence basically tells you whether or not similar code as the one you're looking at here appears in this global threat feed, as well as all the data that you've uploaded to your private Threatray repository. And again, by similar, we always mean code-wise similar. So we're just looking for similar code in this vast repository. It doesn't matter if it has been detected as, in this case, Latrodectus or not beforehand. That works agnostically based on that. We're also not looking for fuzzy hashes or any hashes. We're really using our core technology here. So what we see here in this prevalence tab is that we've seen 55 similar samples within a time span of the last 90 days, and all of them are identified as Latrodectus, some of them even as BruteRatel, which might lead us to see that this kind of attack chain between Latrodectus and BruteRatel is also more prominent and not just a single case. But again, this is primarily intelligence, which leads us to believe that this is again indeed related to Latrodectus. The second part of the intelligence that you get is what we call OSINT Hunt. So OSINT Hunt is very similar to Prevalence, but much more precise and focused. So the global threat feed from Threatray also includes samples that we found and collected from open source intelligence reports. These might be blog posts, tweets, aggregative reports, and so on. And the OSINT Hunt tab basically gives you a list of similar samples that were mentioned by hash in those thread reports. And again, by similar, we mean code-wise similar. So this is highly valuable contextual information. And again, we can kind of use that here to gain additional confidence that the verdict Latrodectus here is really indeed Latrodectus. So here we have this list of similar samples. We could pivot to any of those to look at their analysis. Again, this is subject to the next video, but as you can see here, for example, we have a similar file that was mentioned by this proof point blog post on Latrodectus. We can inspect these reports here directly in the platform, pivot to any of the reports, and also get kind of a list of similar samples that were mentioned by hash in the report that Threatray has analyzed and can relate, again, code-wise to the file we're currently looking at. All right, so now going back to the first tab here, we have now seen on how we identify and detect that this piece of code in this memory region is indeed Latrodectus, and we have also kind of confirmed through intelligence kind of the same verdict that we came to the conclusion beforehand. Now, we've seen beforehand that we have multiple memory regions here. So there's a second one here, which is identified as BruteRatel. Again, we can see that we have some code overlap to what we know as BruteRatel. The AV considers this to be malicious. And in this case here, we don't have any community YARA rules. BruteRatel is also a little bit more difficult to detect and quite often evades AV or YARA rules quite easily. And if we pivot to this tab here on OSINT Hunt, we can also see a couple of similar samples that we have related, for example, in this case here, to a report on BruteRatel. So again, that kind of gives us hints that this is indeed BruteRatel. And lastly, we have another memory region here, which is only detected as malicious by the AV. We have some faint code overlaps here. They are grayed out because they're not large enough to be indicative of this actually being BruteRatel, but might give us hints in that direction. We also, interestingly, have a community YARA hit here saying that this is Bazaar backdoor. Upon further investigation, which isn't part of this video, we found this to be a false positive. So, and again, if we go over to the OSINT Hunt tab, we can see a couple of similar samples that again use this kind of code in different variations. Good. So that was kind of the binary intelligence tab, which really gives you a focused insights on the few pieces of code that really matter for investigation. And we will now go over and have a closer look at what we can see in the full report. So the full report is mostly more indicative or supportive of the behavioral information. So first up, for example, you see a process graph of the execution of this file in the sandboxing environment, and you can kind of see the chain here. Explorer being infected with Latrodectus, run DLL containing some code which is identified as BruteRatel. We also have a dynamic artifact section here, which kind of extracts and displays artifacts that were used during the sandboxing phase. So this covers kind of networking artifacts, IPs that were called, domains, URLs, as well as host-based artifacts. So which files were written, for example, registry value modifications, as well as mutexes here. These values are actually also searchable. So we could search for this mutex here and get a list of samples where this mutex appears as well. Again, this is subject to the next video. And then lastly, we have process and memory details from the execution here. So for example, we have the run DLL here, which kind of indicates what memory has been allocated, at what location, at what point in time. For example, here, again, the same memory region we've seen beforehand. So the information here is the same as you've seen in the binary intelligence tab. It's just positioned or extracted from this process here. Good. So that kind of concludes the first example around Latrodectus and BruteRatel, and should really give you a good impression of what kind of information you can get from an analysis report, how to read it, how to navigate through it. In the second example, we start with a report from Trend Micro on an APT group called Earth Preta, and we have that report open here. They basically talk about the recent campaign from 2024, and it contains a lot of information on the actor, the TTPs, all the different malware tooling. And what kind of caught our attention here is a specific attack chain with some DLL side loading that involves the malware families Doplugs and PlugX. And we're going to focus in this example here on just one of these cases. I'll scroll through some additional information here. So what we're interested in is this particular attack chain here, which they reported as having some Google Drive link that leads to an MSI file, which then is being installed abusing some OneNote launcher, a legitimate OneNote launcher that then sideloads some payloads, decrypts some additional payloads, and then connects back to the CNC server to get even more payloads deployed. Unfortunately, the last stage here on the CNC is not publicly available. The only publicly available files we found is notably this MSI file. So we're just going to take a look at this MSI file through the lens of Threatray and kind of want to see whether or not we can see the sideloading as well as the deployment of these two stages as part of the sideloading, as well as the decryption and execution of the additional payload here. So I got this MSI sample and analyzed that with Threatray, just this MSI here, and we have positive identification for PlugX and Doplugs from our code reuse engines, and we can now take a closer look at the analysis report here. So if we first focus on the binary intelligence part here, we see that we have a DLL file that was extracted from this OneNote's I think that's a OneNote's launcher executable, and it has strong overlaps with this Doplugs family. The AV considers it to be malicious, and we don't have any community auto rule on this particular case here. Furthermore, we also see a couple of memory regions from this OneNote's executable process, all of them identified as PlugX. So here, these are most likely the decrypted secondary stages of this attack. Now, let's straight ahead jump into the full report that will give us a bit more information on the behavioral aspects, which are kind of crucial to understanding the DLL sideloading approach. And if we look at the process graph here, we can clearly see that we have this OneNote executable process, which is infected with the two malware families here. What is interesting in this particular case in the dynamic artifacts are the file artifacts here, where we can clearly see that these three files that we saw in the report beforehand from Trend Micro are being dropped here. They're being created. That's the C here. In the operations, we have this MSI, DLL, the nodelogger.dat, and the OneNote executable. So these are being dropped, and if we then take a closer look at the process and memory details here, we can actually see this OneNote's executable process that was running here. And if we open that, we get more insights on the code that is running in that process. So on one hand, we have the main executable here, the OneNote executable that was brought along as part of this MSI file. Then we have a range of here memory regions that are identified as PlugX. So this is highly likely the encrypted payload that was loaded during execution. And then lastly here we have the MSI DLL, which is the Doplugs implant here, or the backdoor, which was sideloaded. So if you open the first one here, the main image of this process, we can see that AV considers this to be clean, and we can also see that all the code in this binary is considered to be benign by Threatray. So that's a very good sign that this is indeed a benign binary that was simply abused by this attack, same as reported by Trend Micro. If we look at the second stage of the attack, which is the MSI DLL here, we can see, again, similar to, or the same basically, as in the binary intelligence tab, that this is a MSI DLL file that is overlapping strongly with Doplugs here. And if we lastly look at the memory region here, we can see that this is identified as PlugX. The AV even says that this is clean, which isn't the case here. We have some good overlaps again to this PlugX signature, and apparently a lot of the code in this binary is actually non-good code. If we go over to the OSINT Hunt tab, what is super interesting here is you also get a range of similar samples based on finding that in our global repository, and you can see a couple of more OSINT reports that might be interesting here to investigate. So they talk about Mustang Panda's PlugX variants, some Chinese threat actors in SmugX campaign, and so on, right? So this is super helpful, again, to kind of confirm that we are dealing with this PlugX, or kind of the ecosystem of this actor, as well as providing very neat pivot points as part of this particular investigation. Good, so that was rather a quick example here. It also showed you how tracking known good code can be helpful to separate known good from known bad, and being able to kind of focus on particular pieces of code of interest. We saw that we can see this kind of DLL side-loading attack, which is very prevalent nowadays, and see exactly the attack chain from a known good binary to a malicious DLL to decrypting and injecting some additional malicious code. And we've seen that we can basically track the entire attack chain and not just one stage of the attack chain here. In the third and last example here, we are going to look at the file that doesn't have any detections at all. Not from Threatray's code-based signatures, not from an AV, not any community YARA rules. However, in this case, we will be ultimately able to attribute it to HUILoader, which is part of an attack toolkit from an APT group. So we have the sample here, and let's explore how we actually get to being able to attribute that. So all we have here is actually just a DLL file. It has 25 functions. Most of them are benign, and that just leaves us with a couple of functions to potentially use for detection. So not too much going on in this case. And if we switch over to the full report here, we do see the process graph. Doesn't hold much value here. We have exactly 0 artifacts to use. So basically we're again down to exactly this DLL. Maybe a little bit background information here. The reason we have this many DLL processes is because we are basically in the sandboxing mode. We are launching a DLL and trying to kind of fuzz the entry point to exhibit or lure out a specific behavior. But ultimately it's the same DLL everywhere, right? So what is actually helpful in this particular case is the OSINT Hunt tab. So we have a bunch of similar samples that we can find here, from similarities of 100 down to almost 50%. And all of them are actually pointing to this article on HUILoader by the Japanese CERT. So if we open that here, it's an article from 2022, and it discusses a malware known as HUILoader. Has a couple of other malware families that were mentioned here, used by various attack groups since 2015, right? So used to load and execute encoded malware payloads. What is quite nice here is actually we have a couple of similar samples, and the top 2 samples here do have a similarity of 100%. That means the code, or actually these just 5 functions, are exactly the same in the samples that were referenced in the report. So let's try to actually find where these samples were mentioned. Depending on the report, they use these 3 different types of hashes. So that's why we provide all 3 of them. I'll just copy the SHA-2 hash here. Open the blog post. That needs to translate from Japanese to English. And we can see here again the analysis of this HUILoader, which apparently was active since 2015, used all the way up to 2022. And now if we search for the specific hash value that we had in the OSINT Hunt, it will lead us to apparently a HUILoader variant that was discovered in 2015, and matches to 100% to what we were looking at beforehand. So based on that, I could now conclude that this particular sample is probably exactly the same HUILoader from 2015, just a hash different variant. So OSINT in this particular case is super helpful because you can kind of link together, purely based on code and intelligence, link together this unknown file, which had 0 other usable IOCs, to a particular report, and in the report even the particular place where exactly the same sample was mentioned. And that would otherwise, of course, not be possible. Good. So with this, we are at the end of the video already. We saw how we can use Threatray to detect and identify unknown files, especially with its unique code-based approach. And thank you for watching. The upcoming videos will be all around hunting and pivoting as well as reverse engineering, so make sure to watch them as well. Bye bye.